Hi, welcome back to AP Physics 1, Unit 8, Fluids. In this video, we're going to talk about how does fluids and Newton's laws kind of interact. Again, part of this unit is, just talking about how concepts we've already discussed interact with fluids. So in this video, we're going to look at the interaction with Newton's laws. So one thing to remember is Newton's laws, we can use it to describe motion of particles within fluids. The main thing is we're going to look at what is called the buoyant force. So the buoyant force is a net upward force exerted on an object by a fluid. And that buoyant force is very important because it typically will balance out gravity, but if it doesn't get to a point where it balances out the gravity, then that object will sink. If it is greater than gravity, it's going to push it up to the top. But if it's about equal, it's going to stay somewhere in the middle. And this is going to lead us to a very important principle, which helps in ship design. So the buoyant force exerted on an object by a fluid is the result of collective forces exerted on the object by particles making up the fluid. So it's not just one thing that's keeping the object there. It's multiple. It's many forces. So many little forces acting on the object. Okay, so the magnitude of the buoyant force is going to be equal to the weight of the fluid displaced by the object. So we know that weight, right, has an equation of Fg equals mg. But if you remember back to the first video, we talked about how density is mass over volume, okay? But that tells us that mass is equal to volume times density. And so when we look at this, we say it's the weight of the fluid displaced. So this is going to be the density of the fluid and the volume of the fluid, okay? I put W for water. Doesn't have to be water. It can be any fluid. So the buoyant force, F sub B, is equal to rho fluid. We'll keep calling it water just so that we don't get our F's mixed up. So we'll call it rho water, volume water times G, okay? And this right here is known as Archimedes' principle. Now, Archimedes' principle is very important in ship design. It's also the story that Archimedes was challenged by a king to see if his crown was gold. He knew that if he put it into the water that it should sink, but if it didn't, then it was not gold. And lo and behold, the story goes that he yelled Eureka, discovered that it was not gold, and he goes running through the streets in just his bare self. Another area where Archimedes comes into play is he was designing a floating city, and that's what really helped drive this principle, okay? And if you have to draw a free body diagram, right? So you would have the weight of the object going down, but then you have that buoyant force pushing it up, okay? And then that's where we get into the rho Vg, right? Because that's going to be equal to it, especially if it's sitting right on top. If it's greater than, the buoyant force is going to push it up. If it's less than, it's going to cause it to sink. All right, so let's look at an example problem. All right, so A, calculate the buoyant force on a 2-liter helium balloon. And then B, given the mass of the rubber in the balloon is 1.50 kilograms, what is the net vertical force on the balloon if it is let go? Okay, so what we need to do is first find the buoyant force, right? So FB equals rho Vg. Sorry, I can't read my handwriting here. Okay, so we have, first thing we're going to do is convert the 2 liters to cubic meters, and that's easy. 1 liter is 0.001 cubic meters, so 1 liter is 1.0 times 10 to the negative 3 cubic meters. The other thing we need to do, since we're looking at helium, right? We need to figure out the density of helium. So the density of helium is 0.166 kilograms per cubic meter. Sorry, I put a K there. So kilograms per cubic meter. So now we have all the information that we need to plug in. So we have 0.166 times 2 times 10 to the negative 3 times 9.8 or 10, whichever one you want to use. And we find that the buoyant force acting, we are in air. And so we're not going to use the density of helium. I did this in my notes too. We're going to use the density of air. Give me 1 sec to verify. This is on the fly. All right. Okay. So density of air is 1.293. So let me go in and erase this. Oh, sorry, I didn't mean to black it out there. So we're going to go in and erase the 0.166. And we're going to put in 1.293 times the 2. And we find that the buoyant force is going to be 0.025 newtons. Okay, again, we're not going to need the density of helium because the balloon is going to be in air, right? And we're looking for the fluid that we're in. We know it's made of helium, or we know the balloon has helium inside, but it's the air in which it sits. Okay, now we're going to figure out the net force acting on it. Okay, and what's going to happen here is that we're going to have various forces acting, right? So we need to figure out a couple things. One is we have the buoyant force, right? So what forces do we have acting? We have the buoyant force up, right? We have the weight of the balloon, right? But we also have the weight of helium, right? Because the helium it's going to have a certain mass in there, right? And so we would have F net equals the buoyant force minus the balloon minus the helium, okay? So something we do need to figure out is how much helium is there, and this is where our 0.166 number will come in. So we do 0.166 times 2 times 10 to the negative 3. All right, and I'm getting conflicting densities here. I have one written down. So again, we'll do an on the fly. Density of helium so 0.166, okay. And then, so we do 0.166 times 2 e negative 3, and we get 3.32 times 10 to the negative 1, 2, 3, 4 kilograms, okay. So now we have all the information we need to plug in. So 0.025 minus the balloon, so 1.50 times 10 to the negative 3 times 9.8 minus 3.32 times 10 to the negative 4. So I ran out of room here. Times 9.8. And we find that the net force acting on the object is going to be 6. Sorry. Again, all my numbers are jumbled for some reason. So 0.0, there's 2 points, 0.025 minus 1.5 e negative 3 times 9.8. It's not part of the exponent, minus 3.32 exponent negative 4. Not divided by, but times. And we get a number of 7.0 times 10 to the negative 123. And I apologize for all the messiness. Again, my notes were all jumbled for some reason. So we get an answer of 7.0 times 10 to the negative 3 as the net vertical force on the balloon if it is let go. Now, something else they can ask you past this, right, because we're involving Newton's laws, It may ask you for what is the acceleration, okay? Then you would need to divide this by the total mass, and then you can find the acceleration. So the last thing we're going to do in this class is going to be talking about how do the conservation laws come into play with fluids.